Shown in the figure below is an RC circuit driven by an AC power source. This problem is one of the set of AC circuit theory problems, and it's recommended that you view the one called LRC derivation first. Although that is a very long video, it explains the principles that we're going to assume are already understood in performing the calculations here. For part A and B of this problem, we are to calculate the total impedance. Because the resistor and the capacitor are in series, we will take the vector sum of their impedance contributions, which for a resistor is an arrow of length r to the right, and for a capacitor is an arrow of length 1 over omega c directed downward. The resulting total impedance that comes from the vector sum is the hypotenuse of this triangle, and the phase of the impedance is given by this angle. The drawing itself satisfies part A of the problem, and part B requires that we apply the Pythagorean theorem to learn the length of the hypotenuse, which is the magnitude of the impedance. Because numbers for these components have not yet been supplied, this is the entire answer for part B. Similarly, for part C, we are able to determine the phase of the impedance by taking the inverse tangent of the side opposite to the impedance angle divided by the side adjacent. Once again, this result cannot have numbers applied because numbers are not yet supplied in the problem. In part D of the problem, we are to explain in a single sentence what the phase of the impedance means. The phase of the impedance is the phase difference between the applied voltage and the resulting current. In part E, we are finally given a few numbers. The resistance in the circuit will be 1 kiloohm or 1000 ohms. The capacitance will be 0.5 microfarad. The voltage from the power supply, expressed as an RMS quantity, will be 12 volts and will be applied with a frequency of 300 kilohertz. We're asked to determine the RMS current through the circuit, and we'll begin by calculating the impedance. We'll perform this calculation in two steps. First, we'll determine the magnitude of the impedance of the capacitor by calculating 1 over omega c, and with recognition that omega is always 2 pi times the frequency, we're going to come up with a value of 1061 ohms, rounded to the nearest ohm. This result can be plugged into the formula for the impedance that we derived earlier, and when we perform the calculation, we come up with a total of 1458 ohms. Lastly, we simply need to apply the equation that I total is V total divided by Z total, meaning that the magnitude of the total current will be equal to the magnitude of the applied voltage divided by the magnitude of the total impedance of the circuit. This formula is true if all quantities are in RMS, and it is also true when all quantities are in peak. Since we are given an RMS voltage and asked for an RMS current, the calculation is very straightforward and we won't even need to pull out our friend the square root of 2. The result we get, converting it to convenient units, is 8.23 milliamps. In the next part of the problem, we are to determine the RMS voltage across the capacitor alone. In this case, we recognize that the voltage on any circuit element in an AC circuit is the current through that circuit element times the impedance of the circuit element. Because of the fact that the resistor and the capacitor are in series, the current through the resistor is equal to the current through the capacitor and is also equal to the total current through the whole circuit. The previous equation implies a relationship among the magnitudes. The magnitudes can either be peak or RMS, and so far everything in this problem has been RMS, and so we'll be able to plug in the 8.23 milliamps for the current through the capacitor, and using our previous calculation, the impedance just of the capacitor is 1061 ohms. This gives us a result that the RMS voltage across the capacitor will be 8.73 volts. In the last part of the problem, we are actually to imagine having a new circuit, because part G asks us what circuit element we would add to this circuit, i.e. making a new circuit, such that the result was a resonant circuit with a resonant frequency of 30 kilohertz. And we're to specify what kind of circuit element and the value required. Well, what we know is that a resonant circuit is made by having an inductor and a capacitor in the same circuit, and the resonance condition is that the impedance of the capacitor shall be equal to the impedance of the inductor. Solving this formula for the inductance as an unknown results in 1 over the capacitance times the omega squared. Using the given capacitance of half a microfarad and the new frequency of 30 kilohertz, we can calculate the value of inductance required to make the new circuit to be 56.3 microhenries, and that completes the analysis of the problem at hand.